Hello, my name is Harold Park. Today, I'm going to talk about non-causal lifting linearization for nonlinear dynamic systems under model predictive control. The objective of our research is to develop a linear predictive control method for nonlinear systems. Linear models are useful for system analysis, control, and estimation. The nonlinear dynamics can represent a target system with good accuracy, but it requires expensive computational cost. On the other hand, the accuracy of linear dynamics can be lower than nonlinear dynamics, but it is computationally efficient. So many applications would like to use linear formulation for computational cost. For example, the nonlinear dynamics are usually approximated as linear dynamics using Taylor linearization. However, the Taylor linearization is locally valid, so sometimes it can be a problem. For globally valid linear representation, many approaches have been developed. One of them is the Kuhlmann operator. The Kuhlmann operator can be used to represent the nonlinear dynamics as linear in a higher space. The Kuhlmann operator is defined in observable space, which can represent the dynamics as linear. In an observable space, the Kuhlmann operator is linear, but it is possibly infinite dimensional. However, we can obtain an approximate linear model with a finite dimension by truncating the higher dimensional terms. The concept of lifting linearization approach can be shown with this figure. From the original state space, the states are lifted by observable G, and we can obtain the state propagation with a linear operator. So we can approximate the nonlinear state propagation as linear state propagation in a lifted space. But it still requires many lifted states to obtain a sufficiently accurate model. Another lifting linearization is dual-faceted linearization, which leverages knowledge of the nonlinear model physics to choose the auxiliary variable. The auxiliary variable is the same as observable in the Kuhlmann operator. From the nonlinear dynamics, we can choose the nonlinearity as auxiliary variable. The auxiliary variable dynamics are required for linear approximation of the nonlinear dynamics. By taking the derivative to auxiliary variable, we can derive auxiliary variable dynamics. However, another problem is the non-causality in the formulation. So in the previous research, they split the auxiliary variable into state-dependent term and control input term. The matrix du can be obtained using linear regression, and then we can obtain the linear auxiliary variable dynamics using linear regression with H matrices. By augmenting original state with auxiliary variable, we can obtain linear dynamics in a lifted space. This page shows the literature review and contribution of the proposed method. For the Kuhlmann operator, the physical expression is not required, while DFL and proposed method require the physical expression. However, the dimension of lifting space is typically higher for Kuhlmann operator than DFL and proposed method. And additionally, observable choice for Kuhlmann operator is difficult, while DFL and proposed method are easy. And here we can classify the nonlinearity as three cases. First, nonlinear in state, second, control affine, third, control non-affine cases. For Kuhlmann operator, the first case can be approximated as linear. However, the second and third cases are approximated as bilinear and switched linear systems, respectively. So the second and third case requires high computational load. On the other hand, the DFL can approximate second and third case as linear, but it requires additional causality constraint. However, in our proposed method, we can approximate the three cases as linear without causality constraint. The causality constraint can be relaxed with a non-causal formulation. From the observable dynamics, we would like to use this non-causal expression to obtain the observable dynamics. By using the linear regression, we can represent the observable dynamics with H matrices. Here, the dynamics are linear, but it is non-causal. But the idea is our research idea is very simple. We would like to obtain the accurate linear model, and then we will handle the non-causality in the control formulation. The non-causality can be addressed in the MPC formulation, and another benefit from lifting linearization is we can approximate nonlinearities in the cost and constraints. By lifting the nonlinearity in the dynamics, cost function, and constraints, we can formulate linear MPC. The cost function is quadratic formulation, and the dynamics are linear. To handle the non-causality in the linear dynamics, we add to the additional constraint to the control input, the first control input and the last control input. We will show the numerical simulation to validate our proposed method. We will show the two cases. The first one is control affine nonlinear dynamics, and the second is the control non-affine nonlinear dynamics. The first example is the motor example, which comes from the below reference. As you can see in the dynamics, there are bilinear terms x2u and x1u. We will show the predictive validation and then show the control validation with two scenarios. First one is the tracking controller for x1 with no state constraint. Second one is the tracking controller for x2 with a state constraint. This page shows the open loop predictive validation. As you can see, our proposed method is similar to the blue line, which is the nonlinear dynamics. This page shows the open loop predictive validation for several simulation horizons. Our proposed method outperforms other linearizations for long simulation horizons, which implies an MPC with the proposed method can show improved decision-making over long horizon. This page shows the closed-loop control validation with no state constraints. In the upper figure, the gray dotted line shows the tracking reference. As you can see, the blue line and green line shows good tracking performance. In the table, the results are summarized. Our proposed method shows better performance than other linearization method, and the proposed method shows a fraction of computational time compared to nonlinear MPC. The objective of this controller is to track the reference with minimum control input. This page shows the another closed loop controller validation, which is with state constraints. The gray dotted line shows the tracking reference, and the black dotted line shows the state constraints. As you can see, our proposed method shows good performance without constraint violations. In the table, we can see that our proposed method matches the nonlinear MPC at a fraction of computational time. And our proposed method shows better performance than other linearization methods. This page shows the second example, which is control non-affine nonlinear dynamics. As you can see in the dynamics, there are two nonlinearities, sine of x term and sine of u term. We will show the predictive validation, and then we will show the control validation for tracking control with no state constraints. This page shows the open loop predictor validation. As you can see, our proposed method is similar to the blue line, which is nonlinear dynamics. And our proposed method shows a better accuracy than other linearization method. This page shows the closed loop control validation. Here, the objective of controller is to track the reference with a minimum control input. The gray dotted line is the reference, which is over the green and blue line, and in the table summarize the result. As you can see, our proposed method outperforms other linearization method, and our proposed method shows the computational efficiency. And another interesting point here is that the Kuman operator shows unstable behavior. This phenomenon can be observed clearly if we increase the prediction horizon. As you can see, the Kuman operator shows the unstable behavior in X1 and X2. The Kuman operator shows instability with increased prediction horizon or increased simulation time, while our proposed method shows good stable behavior. To conclude our presentation, we developed a non-causal lifting linearization for linear model predictive control. And then we show the predicted accuracy result, which shows our proposed method shows better accuracy than other linearizations. And then we validate the controller performance with other linearization methods. And our proposed method matches nonlinear MPC with a fraction of computational time. And the Kuman operator shows unstable behavior, while our proposed method is stable. Thank you for listening to our presentation. I'll be happy to take any questions.